All right, it's 11:35. Guess we can start. So, Anastasios is a second year PhD student at UC Berkeley, advised by Michael Jordan and Jitendra Malik. Anastasios works on theoretical machine learning with applications in vision and healthcare. We're happy to have you here today and take it away.
Thanks. And thanks for helping organize. Hi, everybody. So, the talk that I'm giving today is titled Distribution Free Risk Controlling Prediction Sets. And long story short, it's about generating rigorous finite sample confidence intervals that work for any machine learning model and any data set and cost essentially no compute. All right, so the distinguishing feature about this set of methods is that they work in a totally black box manner. In other words, you have some machine learning model. It takes inputs and transforms them into outputs. I can give you instance-wise prediction intervals on the outputs without ever touching the model, right? So I never do any special analysis of the model. I never retrain it or anything like that. I just wrap around it. And then I can give you a procedure that gives you like uncertainty bars or error bars on your estimates. Okay. So I'm gonna teach you how to do that. I'm gonna give a tutorial style presentation, starting with a precursor method to this one called conformal prediction, which some of you already know about. But it's gonna be basically, a chalk talk. So because it's a chalk talk, I always request this. Those of you that are able to turn on your videos, and it's okay if you can't, but those of you that are able, I would appreciate it if you turned it on. Because what I do is while the talk goes on, I watch you. And then if you're going like this, then I'll move on. But if you're like this or like this, then I don't. And I'll take a little more time to make sure we all get it. Okay, so let's move. These are my co-authors on this project. These are my advisors, Jitendra and Mike. And these two guys are awesome. Stephen and Li Hua were both at some point students of Mike and Emmanuel Candez at some point in their careers. Okay, so let's talk about error bars. Why do we even want error bars for machine learning models? Well, it's because we're going to use these sort of black box models for decision making downstream at some point. So my motivating example for this is imagine that you're a doctor, and I give you a computer vision classifier that acts on MRI images. Okay, well, what would you want the classifier to give you? One thing that you'd want it to give you is the top one softmax score, sort of like the model's point estimate of what disease the person has. The model thinks somebody's normal. Okay, but that's actually not the most useful thing to use as a doctor because you don't know how reliable the algorithm is, right? And you care that there's like a 5% chance that the person has cancer because your job as a doctor is to rule in or rule out harmful diagnoses with high probability. Okay, so one useful output that you could get is like a set of plausible diagnoses along with a guarantee. Okay, so for example, a set of diagnoses based on the output of the model that's guaranteed to contain the true diagnosis with high probability. All right, so if that set only contains normal, then you're basically good. But if that set's large, right, and if it contains something like cancer, then maybe you do a differential diagnosis based on those diseases and you get more information. And so that becomes a useful output to you. Okay. Another situation where you might want such prediction sets, a slightly different setting is, let's say we're doing some sort of like a tumor segmentation problem. Right, so the input here is an image of a gut polyp, and the output would be a segmentation map that says here's where the polyp is. Right, and here I've color-coded it a little bit differently. So blue pixels are like false positives, white pixels are true positives, black pixels are true negatives, and red pixels are false negatives. Right, so the predicted tumor is blue plus white. And I can also give you sets that have a different type of probabilistic guarantee, sets that contain 99% of the tumor with high probability. Okay, so this talk is going to be about generating sets like these, sets of classes that are guaranteed to contain the true class with high probability, sets of pixels that are guaranteed to contain the true tumor with high probability, and these guarantees are going to hold no matter what segmentation model you use, no matter what classifier you use. Yeah, so that's the basic idea. before we get into some concrete instantiations of this problem, does anyone have any questions? No. All right. Let's move. Okay, so let's start with the classification problem, since it was our first motivating example and it's also an easy setting. Okay, so in classification, what is our goal? Our goal is we are given a calibration data set. Okay, so we're going to use some holdout data here. This is fresh data that the model has not seen yet. All right, so it's like a sequence of paired images and classes. It doesn't need to be images, right? But let's just think about image processing for this motivating example. It's a sequence of pairs of images and classes, and there's n of them, where n is like something like 1,000, right? It actually works for any n, but let's just imagine we have sort of this size of data set, and they're drawn from some probability distribution IID. And it doesn't actually need to be IID, it can be exchangeable, but sort of a technical condition. Think about it as IID data. And then we have a model. Okay, the model is pi hat sub y of x, right? And this is just my notation for an estimator of the conditional distribution of the labels given the input, okay? So this guy estimates probability y equals y given x equals x. But you don't know how good it is. It can be bad, right? So this is your neural network. It may be terrible. And then I take a new image, x sub n plus 1, and predict a set, okay? So T takes an x sub n plus 1, and it outputs a subset of your label space, right? So it outputs a set of classes, in other words. And I want you to give me a guarantee about that set. Okay, so I want you to guarantee me that I contain the true class y sub n plus 1, which is unknown to you, with high probability. Okay, so this is called coverage. All right, so let's parse this guarantee because it'll be important later. So this guarantee is saying the probability that I contain the true label, which is unknown to me at test time, in my prediction set based on the new sample is greater than or equal to 1 minus alpha. Okay, you get to choose alpha. Alpha is like your error rate. If alpha's 0.1, this is 90%. And then I guarantee that the true diagnosis is in the set of labels with high probability. Okay, so this is called, when there's a greater than or equal to sign here, it's called conservative coverage. When there's an equal to sign here, it's called exact coverage. Okay. And before we move on, just notice, in this guarantee, there's nothing about your model, right? I've never said anything about your machine learning model. So where is it? Your machine learning model is used in this function. Okay, so this set valued function uses your machine learning model as a substep, right? So an example of this might be the softmax scores of your machine learning model are used in T. Okay. So let's think a little bit more about what these sets look like, what properties we want them to have. So here I've just taken 3 squirrels from ImageNet. Okay, so this is an easy squirrel. Oops. This is an easy squirrel. This is a medium squirrel, and this is a hard squirrel. Okay, so why is this guy an easy squirrel? It's because its background makes sense. Squirrel's on a fence. Its body's in plain view. You've seen the model has seen a lot of squirrels like this. So the set is of size 1. Okay, so I give you a prediction set that only has 1 element in it because the model's really sure. So my confidence interval, so to speak, doesn't need to be large. It can be tight. But when I'm unsure, so this guy here, his head's cut off, his background doesn't make any, at least it doesn't suggest, the background does not suggest that this is a squirrel. And in fact, I do not actually think this is a squirrel. I think that this is a marmot. And so does the model. But in any case, the set is large, right? Because the model's unsure about what this guy is. All right? So in other words, our objectives are, the first objective for these sets is basically nearly exact coverage, right? We want the probabilistic guarantee to hold. Otherwise, there's no point in doing any of this. We actually want the guarantee to hold rigorously, no matter what your model is or the nature of your data. The second thing that you might want from your sets is basically small size, right? Just like you want a tight confidence interval, you might want sets of small size because they're useful to you as a decision maker, right? One way to get exact coverage is to output the entire label space with probability 1 minus alpha and nothing with probability alpha. And that's like, that's a way of generating prediction sets, but they're huge and they're totally not useful. And moreover, they're not adaptive, meaning these sort of like random prediction sets they're not dependent on your input, right? So what you'd like is for the sets to be small for easy examples and big for hard examples, so that the size of the set gives you a signal about how hard things are. Okay, so those were basically our 3 objectives about prediction sets. All right, this is another example that I did on a COVID data set. But now we're going to get into some concrete procedures for how to generate them. Okay, so now we've motivated the problem. We've talked about prediction sets. This is a good time to ask any questions that you have about prediction sets.
I was wondering if the data sets vary in okay, so I know the goal is like distribution free, but do the data sets vary in like certain things like lighting or something to that nature? I noticed that they kind of vary in position of, I guess, like the way the camera is pointed at the animal, but yeah.
Yeah. So the answer to that question is that the types of sets that I'm going to be able to give you, the guarantee does hold in a distribution free way if the data that you get in this data set, this calibration data set, is representative of the new data point that you're going to get later, then this procedure is going to work. And by representative, I mean, let's say like we're talking about natural images, right? If this set of data points has that sort of variation in pose or lighting or whatever that you would expect from a new data point, then the guarantees will hold. Now, if your entire calibration data set is taken at one illumination level, and then you give me a test point that's at, a totally different illumination level, and those are sort of deterministically different, then the guarantee doesn't necessarily hold. Right? But if that randomness is just sort of a property of your data generating process, then yes, the dataset is definitely the dataset can definitely incorporate such variations. Does that answer your question?
Yeah, that was great. Thank you.
Great, thanks. Okay, now let's talk about some concrete procedures. So some of you have probably already thought of the following procedure, okay? So I'm calling this the naive procedure. And the naive procedure is to do the following. First, I'm going to, perform some calibration scheme on my model, like Platt scaling. Right? So I take my classifier, I do Platt scaling on it. If you don't know what Platt scaling is, it's okay. It's not really actually consequential. The second thing that you do is you sort your softmax scores from most to least likely. Okay? So I look at the most likely class, the second most likely class, etc. And then I sort of greedily include those in my prediction set up until my total softmax mass exceeds 90%. Okay? So this is my little pictorial representation of it. I start at the most likely class, which is order statistic 1, right? I take the first, second, third most likely class up until I just exceed 90%, and then I stop. Okay? And this is based on the estimated probabilities output by the model. Right? So these are the softmax scores. But it turns out that this procedure fails. Okay? And this procedure fails because you do not know that your model is any good. Right? Your model may be arbitrarily bad. I haven't told you that your model's not white noise. Right? So this procedure may just be outputting. Actually, in the case of white noise, it might work because it's like if it's independent, then that might actually work. But, I haven't told you that your model's not pathologically wrong. So For that reason, you can't really perform this procedure and expect it to work. Okay? So conformal prediction is basically a way to fix this. All right? And so conformal prediction basically says, what if, instead of doing this naive procedure where we took the softmax scores of the model as sort of given to us, as true, what if we learn instead a rule to predict sets based on our calibration data? Okay, so instead of saying we're going to put 90% here, we're going to believe the scores of the model, we're going to use a different procedure or put a different number there that's learned from our data such that our prediction sets actually rigorously contain the true label. Okay? And we're going to use our calibration set to do that. So let's show you the exact procedure. This is an example of a conformal procedure. The conformal prediction is actually a family of procedures, but I'm going to show you the simplest one. Okay? So the first thing you're going to do is you're going to get the score of the correct class for every example in your calibration data set. Okay? So what I've done here is on the x-axis, it's like, every class. The softmax, this is the plot of the softmax output of every class when, x sub I is put through your neural network. So I calculate neural network of x sub I, and then that's a vector of softmax scores, right? 0.1, 0.2, 0.005, or whatever. And then I've just plotted those here. Okay? And then I look at the score of the correct class. And I know this because this is from my calibration data set, right? This is from the fresh data that the model hasn't seen. And so I know the softmax output for that class. And that level, I'm going to call E sub I. Okay? So the score of the true class is going to be E sub I. Now, because I have a whole calibration data set, I have a whole sequence of these, right? I have I equals 1 through n of the E sub i's. In other words, I have the score of the correct class for everything in my calibration data set, right? Nice. So I've collected these in a bag, and I'm going to move on to step 2. All right, in step 2, what I do is I calculate the roughly I calculate the 10% quantile of those E sub i's. Okay? It's not actually the 10% quantile. There's a very small finite sample correction. But it's roughly the 10% quantile of the E sub i's. All right, and I call that Q hat. So let's just really quickly in English say what Q hat is. Q hat is the score such that at least 90% of examples have their true class with a score above Q hat. Okay, so I've made a little plot of it here. But basically, what I've said is, here, I'm going to erase that. This is like a histogram of all your E sub i's, right? So I've taken your E sub i's and made them a histogram. E sub i's. And now I picked Q hat to be roughly the 10% quantile, which means I picked Q hat so that roughly 10% of the mass is below Q hat. Okay, so if n were infinite, what would I expect? If n were infinite, Q hat would be the true 10% quantile. And then I would expect that if you gave me a new example, the softmax score of the true class of that new example would land in this area, in this region, with 90% probability. But n is not infinite, right? And so that's why we did a slight correction. We're going to do a slight finite sample correction that I'm not going to show because it's actually almost nothing. Although it is sort of some of the magic behind conformal prediction. Okay, so we took the 10% quantile. And now we're basically done. Now we can form prediction sets, okay? So my prediction sets are going to be, my T from before. This is going to be the set of all classes whose score exceeds Q hat when x sub n plus 1 is input. Okay? In other words, I'm going to calculate my neural network of x sub n plus 1. And then I look at all the softmax scores, right? So this is the plot of the softmax scores for each class, 1, 2, 3, 4, 5. And then I look at the level Q hat that I took from step 2. And every class that exceeds that level, I'm going to include in a prediction set. Okay? And it turns out that when you do this, you have a valid prediction set. You have a prediction set that has the guarantees that we talked about earlier on in the talk. In other words, the prediction set achieves coverage, right? Achieves conservative coverage. But also, you get something kind of magical. Okay? And the kind of magical thing is that you get, in addition to the lower bound, in addition to saying I contain the label with the right probability, you also get a matching upper bound that says that my set is not too conservative, except as scaling with 1 over the size of your calibration set. Okay? In other words, if n is 100, then I'm not going to contain the true label with more than 91% probability, which means my set is basically as small as it can be while still achieving coverage. And this guarantee holds for any algorithm, any data set, any level alpha, any n. Okay? Any questions here?
Yeah, this calibration set, does it need to be independent from your training data for this model?
Yeah. So usually the way that you do this in practice, so the problem, of course, if you use the training data for the calibration data is that your model may be overfit on the training data, and thus it's no longer representative of a new test point. In practice, what you actually do is you take your training set, which is, usually pretty large, and you just like carve off a tiny fraction of it for calibration, like, 500 or 1,000 data points. And then you just keep that data as fresh data. Okay, any more questions here?
What assumption are you making here?
The only assumption that you need to make in order for this to hold is that the calibration data set that you ran this procedure on is exchangeable with this new data point. Okay? Or, IID implies exchangeability, so think about it as IID. If this data set is IID with this new data point, then this guarantee will hold.
Okay, thanks.
Yep. Okay. So conformal prediction is an awesome technique. It was originated by this guy, Vladimir Vovk, who's at Royal Holloway University in Britain. And he's a student of Kolmogorov. So this comes from like an old group of probabilists, basically, like the inventors of probability. But conformal prediction also has certain problems. So I'm going to skip this slide. Conformal prediction has certain sort of pathological problems. For high dimensional examples, for high dimensional Y, basically, for high dimensional outputs. And it also can't handle the cases where different errors cost different amounts. Okay, so just concretely, imagine if you're the doctor in our original example, and you cared more about getting the class, stroke correct than getting the class concussion correct or getting the class normal correct, then conformal prediction doesn't really handle that notion of error, right? Conformal prediction is just 0, 1. My example is in the set or it's not in the set. All right. So that's one sort of, limitation of conformal. And it also has problems for high dimensional outputs. So let's make that a little bit more concrete here. So what I've done here is I've taken the segmentation model that we talked about before, and I've output prediction sets using conformal. Okay, so how did I form these prediction sets? This is a set of pixels that I used conformal on to guarantee that the set of pixels contains the tumor with 90% probability. Okay, so what do I mean by that? I mean, what I did is, with a segmentation model as an intermediate step, usually what happens is that for each pixel, I give you a score between 0 and 1. Right? A score between 0 and 1 that tells you like what the probability is that that pixel is a tumor. And so what I've done here in this little diagram is I've taken like, a one-dimensional slice of my tissue, and I've just sort of illustrated the model's probability of tumor. The estimated probability of that, each pixel in that slice being tumor here. And then if you threshold that at a particular level, right, then I can give you like all the pixels that have estimated probability above that level are going to be estimated to be tumor. And below that level, no. Right? So that basically with Conformal, I tuned this level so that the sets of pixels are guaranteed to contain the tumor with high probability. Okay? And so just to remind you here, so I picked a threshold above which, if the model's confident enough that this is a tumor pixel, then I'm going to classify it as a tumor pixel. And then I use Conformal to tune that threshold so that it contains the tumor with high enough probability. Now, if you look here, remember that the blues are false positives and the whites are true positives. Right? So white plus blue is my estimate of the segmentation of the tumor. And so these sets are essentially totally useless. Right? This is a useless output. It's taking basically the whole image every time. Why? Why is that? Well, it's because Conformal is giving you exactly what you asked for, which is that I contain the tumor with 90% probability. But if you look here, you see that little slice of red? This guy. This is a miscoverage event. This set does not contain the tumor because a tiny fraction of the tumor is outside the set. Right? So I missed a couple pixels here. So the tumor's not in the set, and I marked this whole example wrong. And the same thing is actually true of this guy. So I marked this guy and this guy wrong. There's 20 examples on the page. 2 of them are wrong. I've given you 90% coverage. Ta-da. Okay, so Conformal is giving you what you asked for. It's just that what you asked for is really conservative. And so why is it conservative? Why actually do both of these phenomena happen? They happen because if you take, so this is sort of like miscoverage, right? So coverage would be the probability y is in the set is greater than or equal to 1 minus alpha. This is y is not in the set, right? So you decompose that as an expectation of an indicator. And what you get is basically, you can just observe that this quantity is a risk, right? It is the expected value of a loss. It's a risk. Where in this case, the loss is a 0, 1 valued loss that takes on the value 1 if the label's not in the set, and 0 if it is. So I'm going to throw you a loss of 1. I'm going to say you're bad if the label is not in the set, and you're good otherwise. All right, and the expected value of that, I'm going to control it. That's what conformal prediction says. Okay, and the idea of risk controlling prediction sets, which is the main purpose of this talk, is to replace this loss with another one. Okay, with actually, an arbitrary loss. Now, in order to do that, you kind of need to take apart conformal prediction, because conformal prediction really, like the mathematical arguments of conformal prediction really rely on the fact that this loss is 0, 1, because there are like a bunch of binomial arguments under the hood. And so instead of using those binomial arguments, we're going to use concentration arguments. But nonetheless, we're going to be able to get a bunch of sort of the positives of conformal prediction, which include finite sample guarantees that work for any model and any distribution. But we're also going to be able to do certain things that conformal can't do, right? So for example, we're going to be able to replace this with a loss like the false negative rate, which is going to solve our tumor problem. And we're going to be able to incorporate the cases where different mistakes cost different amounts. Okay, and so when you do this with risk controlling prediction sets, roughly what I've done here is I've controlled the false negative rate, so I contain 99% of the tumor with 90% probability. In other words, I allow you that little freedom to make a small error. But in return, I give you sets that are much more manageable. Right? So this is actually a useful decision-making output in contrast to the other one.
Can I ask a quick question?
Yeah, please. This is a perfect time.
So in the first example, what you've done is you've selected, so the model's outputting like a probability for each pixel, and you've selected the threshold at which that the model will output true for cover every true positive.
Yeah.
And then you've taken that threshold for each picture and used the conformal method to select like the overall threshold that you need.
Yes.
And what you're saying is that is extremely low, I guess, and so basically every image is always covered.
Exactly. It becomes very low.
And so what happens if you, instead of, so I guess like the next thing to do would just be, instead of trying to cover every single image of the tumor, you could just say, oh, here's my false negative rate. I'm just gonna pick the threshold that gives me 95% of the tumor in each image. And I don't, like, depending on how the model, I don't know if this gives you the same theoretical guarantees, and I guess it doesn't. Or
yeah, so what you're saying is exactly sort of the right intuition to have, and that is in fact what you should do, and that's what these things do. It's just that in order to get the theoretical guarantees, you can get them, but you need to kind of rework some of the math.
I see.
Right? So you can't do this like taking quantiles of scores thing that we did in our earlier conformal prediction procedure. You can't do that exactly. You need to do a modification of it in order to get the theoretical guarantees to pass through. And so I'll show you basically exactly what that modification is in a second, but you have the right idea. That's the procedure that we're going to talk about.
Okay, got it. Thanks.
Yeah, no worries. Any other questions here?
Oh, wait, sorry. And this for like the image classification, this doesn't really help, right? Because your model's just okay.
I would say, yeah. I mean, like, unless you're interested in a more refined notion of error control in the classification setting. So unless you're interested in, for example, controlling a risk, a classification risk where different errors cost different amounts.
I mean, this could help you if you're using like an ensemble method, right? Maybe it's like a more principled voting mechanism.
Actually, I think that's true. Although we won't discuss the way that I think that can happen in this talk, but I think that you're right about that.
Okay.
Yeah.
Cool. Yeah. Thanks.
Yeah. Thank you. Okay. So just to review, instead of using the 0-1 loss here, I use the false negative rate. I've just written, 1 minus the false negative rate here. Okay. Now let's talk about how we get this procedure. As we talked about before, the fundamentals of our procedure is going to be our model outputs a curve, right? So I've taken a one-dimensional slice of tissue. Our model outputs a probability that any part of the slice is a tumor, and then I threshold that at some level, right? So I'm taking super level sets of this function that my model outputs, of the output of my segmentation model. All right. And so you can think about this basically as like a tunable, like a parametrizable family of sets that is given to you by your model, right? And I've written this parametric family up here. It's parameterized by this level lambda. Okay. So I've written when lambda equals negative 0.7, I'm going to take the 0.7 super level set of this function. In other words, all pixels that have score above 0.7. Okay, and the negative thing is dumb. I'll show you why that's happening in a moment. And then when lambda equals negative 0.3, I'm going to take the 0.3 super level set. Okay, so all things that are above the level 0.3 estimated score are going to be in my prediction set. All right. So tuning lambda is now our problem. And we're going to tune lambda based on our calibration data in order to try and choose the smallest lambda, right? The smallest meaning more negative. so I'm going to take fewer things. I'm going to pick the smallest lambda that's guaranteed to upper bound the risk. All right, in a sense that I'm going to tell you in a second. Okay, and this has the same benefits of conformal in the sense that it's adaptive, right? For a very difficult example, what does a very difficult example look like in this case? A very difficult tumor looks like this. Stuff's like uniformly distributed and I can't tell where it is. In that case, my level is going to be like here, and I'm going to take the entire image. And for a very easy tumor, which looks like this, my level is going to be at the same spot, but I'm only going to take a little bit. Right? So we're still adaptive. We're adaptive to the difficulty of the tumor. Okay? So just to do a little bit of resetting here, before we get into the concrete procedure for how you do this, we have our calibration data, right? We're going to predict a set. This time the set is actually, it doesn't necessarily need to be a subset of Y. It can be an element of Y, right? Because Y, like script Y is a set of sets, right? It's a set of prediction sets. Sets of pixels correspond to tumors. So we're going to predict a set, and it's going to control a loss, right? So we have to pick a loss in advance. The loss is some function that takes in the true label, in other words, the true segmentation map, and then your prediction set. And it quantifies how far away the prediction set is from the segmentation mask. All right, so it puts a number on it. An example would be the 0-1 loss. Another example would be the false negative rate. And there's all sorts of exotic things that you can put here. And then we're going to guarantee you the following. I'm going to be able to give you a prediction set, just like before, right? The prediction set takes in a new test point, and then it guarantees you that the risk, right? The probability that the risk is greater than gamma. Gamma is some desired error level, right? So you get to pick gamma. Gamma is how much risk am I willing to tolerate? The probability that my risk is greater than gamma is less than or equal to delta. So the probability that I violate the risk guarantee that you asked for is small. Right? And this is a property of T. Right? So T is going to generate sets like this. And when you do that, T will be called a gamma delta risk controlling prediction set. Right? So that's what a risk controlling prediction set is. So how do we make T? Right? The question is, how do we make T? Okay? And so what do we need to make T? We need three things. All right? The first thing we've already talked about. It's a family of nested sets parameterized by lambda. Okay? So what do I mean by nested sets? I mean that when lambda grows, the sets also grow. Large lambda, large sets. Right, so this is why I made lambda negative in the example earlier. It's because small lambda, like lambda equals -1, is going to give you nothing. Large lambda, like lambda equals 0, is going to give you the entire image. Right, and then you interpolate in between as you move. But larger lambda leads to larger sets. The second thing I need is a monotonic loss function. Okay, and it's set monotonic in the sense that as your prediction set grows, your loss only shrinks. In other words, like the false negative rate, you know, as I include more pixels in my prediction set, the fraction of the tumor that I miss only goes down. Okay, so this is a monotonic loss function. And then the third ingredient, which is kind of out of the box, right? You don't necessarily need to choose this, is a pointwise upper confidence bound. So this would be something like Hufting's inequality. Right? And the pointwise upper confidence bound says that the probability that my true risk at level lambda, so by R of lambda, I mean, you know, the expected value of the loss of T sub lambda of X. Right? So that's what I mean by R of lambda. It's the risk at level lambda, right? When I choose the threshold lambda, what is my risk? The probability that the true risk at level lambda is less than or equal to the upper confidence bound on the risk at level lambda is greater than or equal to 1 minus delta. Okay, so this is like Hufting's inequality can give you this. All right, this is what the family of nested sets looks like in the tumor problem, right? So for small lambda, I give you small sets, and for large lambda, I give you large sets. And so now let's imagine we have these three things. We've already talked about how to get, I guess, the first and the second, the nested sets and the loss. The third thing is the upper confidence bound. We're going to defer talking about that for a moment and just imagine that we have it. So imagine that we have a valid upper confidence bound on the risk. Then how do we choose lambda? This is how. It's actually really simple. What you do is you start with large lambda. So the gold curve is the upper confidence bound on the risk, right? The black curve is sort of the true risk. And it's monotonic because my loss is monotonic. Now what I do is I start on the right-hand side. I start with large sets. And then I make them smaller and smaller and smaller up until my upper confidence bound on my risk just exceeds gamma, which is the desired risk level that you asked for. Right? This is the parameter that you put into the problem. And then I stop. Okay? So concretely, let's say gamma is like 0.01. That would mean I ask you for prediction sets that contain 99% of the tumor, right? 1 minus 0.1 is 99%. So I ask you for prediction sets that contain 99% of the tumor. Then I calculate let's say the empirical risk, and then I put an upper confidence bound on it that holds with 90% probability using Hufting's inequality. Then I start at large sets, and I make them smaller and smaller up until I reach gamma, up until I violate. And then I pick that as my lambda hat. And then I can use lambda hat forever. Lambda hat becomes my level. So now when new examples come in, I calculate the sort of probability that each section of the tissue is a tumor. I threshold them at level lambda hat, and those are my prediction sets. Those are like the prediction sets I showed you before. Okay? And there's a proof of this that we'll skip because it's, first of all, it's easy. Second of all, just believe me. And we can talk about it later. Okay. So on real tumor data, what would you do? Just to emphasize this, what you would do is the first thing is you would calculate your empirical risk. So what is your empirical risk? It's the average loss of your prediction sets at level lambda, right? So when I threshold at level lambda, I get prediction sets that look something like this. Now, what is the loss of each example? What's let's say, the empirical false negative proportion, right, of my prediction set? I do that for each example. I take the average. That's R hat. Now, it turns out that with Hufting's inequality, if you set R hat plus to be just the empirical risk plus this constant, right? This is a special constant that Hufting came up with. Then you're guaranteed that the probability the upper confidence bound is less than the true risk is less than delta, right? So this is indeed a valid upper confidence bound. It holds probabilistically. And then what do you do to create your prediction sets? And these are actually the plots from the tumor example. Okay, so this is what your data looks like. You look at the orange curve. That's our Hufting procedure. You start at large sets and you move to small sets up until you reach your level gamma. And then you stop, that becomes lambda hat Hufting. Okay. Now, in practice, we don't actually use Hufting. Why don't we use Hufting? Because Hufting's not tight. You want a better concentration bound. What does a better concentration bound gives you? It gets you closer to the blue curve. So it decreases the distance between orange and blue. And what that does for you it allows you to go farther left until you pick lambda, which gives you smaller sets. Smaller lambda, smaller sets. The farther left I can go, the better it is. All right? Everybody with me at this point? Nice. Okay. So now obviously we don't use Hufting's inequality, as I said. What we use is actually a variance adaptive concentration bound that Ian Wadby-Smith and Aditya Ramdas came up with. But I don't think we should talk about this. It's actually not particularly, it's just complicated concentration bounds that give you really tight performance. And it's really beautiful. But you can substitute any concentration bound in here. Pick your favorite concentration bound, and this procedure will work. But this one's really nice. We can talk about it later if people have questions. Okay, so I have to confess something, which is that I lied earlier. And these tumor segmentations don't actually control the false negative rate. They control something that's slightly different, slightly more exotic. Okay, so they actually control the average false negative rate per tumor. The average false negative rate per tumor. And so what I mean by that is, let's say I have an image that has multiple tumors in it. The behavior that I want to avoid is that I want my algorithm to avoid taking like all of one tumor and missing all of another. Right? I want to like make sure that I contain 90% of each tumor in each image with high probability. Okay? So instead of the false negative rate, I choose, well, H is my connected components function, right? So I define different tumors as different connected components in the image. And then I just take the average. So this is the false negative rate. And I take the average false negative rate per tumor, where the tumor is defined as the connected component, right? Okay? And then I also don't threshold the probabilities directly, right? So I don't do exactly the procedure that I just take the model's output as given and then threshold like this. What I do is if I see a second peak, I renormalize it a little bit so that I'm like taking more of its mass and I don't need to choose a really low level. Okay? So I do a little bit of like, and I do this with like dilation and stuff and like peak finding and old computer vision algorithms from when Jitendra was a kid. Okay, so we're in the examples section now. I'm going to show a couple more examples before the end of the talk. But any questions so far? Good. Let's keep going. So another example where you might use risk controlling prediction sets is in multi-label classification, right? So our input in this case is an image, and our output is a set of classes. And I'm going to guarantee you that the set of classes contains 90% of the true classes that are actually in the image. Right? So I'm going to use the false negative rate again. I'm going to tell you the set contains most of what you wanted. Okay? So I'm using MS Coco here, which is a big computer vision data set. There's 80 possible classes, and the model, the prediction engine, just outputs like a sigmoid score for each class. Right? So it's between 0 and 1. There's a 0, 1 valued response for each of the 80 classes. And I just do this thresholding procedure again. The same thing for the tumor. Now we're discrete, but who cares? The loss that I control is the false negative rate. And the sequence of nested sets is just like it was for the tumor, right? So there's, instead of having a continuous curve, we now have bars like this. And the sequence of nested sets is, when lambda is small, I pick only the tallest bars. And when lambda is large, I pick more of them. And then the prediction set will be discrete, etc. And this is the performance of that procedure. So it's pretty reasonable. I like this. I like this one because it's really clear that like alpaca is not an MS Coco class, apparently. Because the distinguishing feature of this image is an alpaca, but it's nowhere in here. But it gets the horse. And it misses the car. But nonetheless, the prediction sets are pretty good. It sort of picks the right level. And these prediction sets are guaranteed to contain 90% of the true labels with 90% probability. I also did a conformal baseline here just to show you that it's more conservative. We're not going to delve too deep into these plots, but if you look at the risk here, this is 3 different versions of risk controlling prediction sets with different concentration inequalities. And this is exactly the behavior that we wanted, right? That like our empirical risk is only violated with about 10% probability. Right? So this is our risk over different like resamplings of the data. And it's only above the gray line, which is gamma, with delta probability. Whereas conformal is very conservative. Takes bigger sets. So I guess the last example that I'll present is on hierarchical classification. So in hierarchical classification, our input's an image and our output's an interior node of the label tree. In other words, let's say our classifier sees some sort of a dog. It sees a speckled, spotted, spaniel, beagle, something. But it's not sure that it's that breed. It's just sure that it's a dog. Well, in that case, I want my classifier to output dog, not something more specific than it knows. Okay? So this is in basically the setting where our labels are part of a tree, right? And I want to pick an interior node of the tree instead of picking a leaf node. All right? So I'm just going to use ImageNet for this because there's already a label tree called WordNet that works for ImageNet. So our setting is y is in 1 through 1,000. So we're in the single class setting again. And our model outputs softmax scores, right? So they normalize between 0 to sum to 1. And the loss that I'm going to control here is actually a loss on the tree. So I'm going to be able to guarantee you that my prediction set, in this case, my prediction set is spaniel. My model thought it was a Cocker Spaniel. That's the top class. It wasn't sure, so it said my prediction set is going to be spaniel. But the true class was actually Siamese cat. Okay? And the loss that I can control is I can guarantee you that I give you prediction sets that are, let's say, no more than 2 hops along the graph away from any ancestor of y with 90% probability. In other words, they're like not too far off from the correct answer in like tree distance. Okay? And so now we have our loss. How do we get our nested sets? Our nested sets work like this. We start from the most likely class as estimated by the model. And then we just travel up the tree until we reach the root. Okay? And for each interior node, how do I index it? I pick its lambda to be the sum of all of the softmax mass of its leaves. All right, so there's sort of a duality here between prediction sets of leaves and interior nodes on the tree. Right? Okay. And here's what the outputs look like. So just focusing on this one for a second. The true class was consomme, I don't know. Consomme. My model thought it was a hot pot, which is wrong. But using this procedure, you can get dish, which is true. It is in fact a dish. All right, so what did it do? The model thought it was hot pot, but it wasn't confident enough. So it went up to stew, and then it went up to dish. And then the sum of all of these softmax scores was sufficient to exceed lambda, so I stopped. Sorry, it's sufficient to exceed, exceed lambda. So I stopped. Lambda hat, the chosen lambda based on the concentration bound. All right. And then I got valid prediction sets. Valid in this case means that they're no more than 2 hops away on the graph from the correct, from an ancestor of the correct label with high probability. Okay. I have a third example here, but I don't think we should go over it. It's a protein folding example. It's basically a multidimensional version of our regression problems from before. So it's just kind of cool. You know, you do biology. It's like you feel like a scientist. Okay, that's the end of the talk. I did want to tell you guys that there's going to be a workshop, if you guys are interested on this topic, on distribution-free uncertainty quantification at ICML. And I'll put the link for that in the chat. Come, everybody's welcome. Okay.
Thank you. Are there any more questions? There's one in the chat.
Okay.
Can you see it?
Yeah, I do. Okay. Stephen is wondering, what is the relationship between conformal prediction and confidence estimate in a Bayesian neural network with approaches such as MC dropout, Bayes by backprop, and deep ensemble? Okay. So theoretically, there's no relationship between these two topics, right? They just come from different areas. However, you can. So the problem with the Bayesian methods is that, you know, the uncertainty estimates that they give you are not necessarily any good, right? You've trained them on data, but there's no guarantee that like your ensemble or like your dropout is like actually quantiles, right? Of the distribution that you care about. I mean, there are some theoretical guarantees, but they only hold like if your model's well specified and blah blah blah. But what you can do is use those Bayesian methods as inputs to conformal prediction. So what conformal prediction can't do, conformal prediction cannot give you a good heuristic notion of uncertainty to begin with. But what it can do is it can take any heuristic notion of uncertainty that you give me and turn it into a valid prediction interval. So what you would do with these Bayesian methods is that you would use them as input to procedures like I've talked about today, and they would likely perform quite well in terms of generating you prediction intervals. Now, there was this paper recently by Peter Hoff that showed that if you take the posterior predictive distribution of a Bayesian model and use that as your score, then you get sets that are frequentist and Bayesian. In other words, among all, I guess, prediction sets that have frequentist coverage, they are Bayes optimal. So there are some connections, but that's the long answer.